Thank you very much for the kind introduction, Nick. Can you all hear okay in the back of the room? So thank you very much for coming to this session. As Nick said, my name is Eric Kessler. I'm running the science team at Amazon Braket, the quantum computing service by AWS. We launched Amazon Braket now 5 years ago with the goal back then to make quantum computing resources as accessible as other compute resources and compute options on AWS. And in the next 30 to 40 minutes, I will talk about what we have learned over that time, where the industry is at today, and how we see quantum computing fit into the scientific compute stack in the future. I'm particularly excited to be here at GTC because we share a lot of the views on the challenges and opportunities in this question around the quantum computing stack, how it fits together with our friends from NVIDIA. And we've started collaborating with the NVIDIA teams over the last year, and we're happy to share some of the things that we have done. But of course, the relationship between AWS and NVIDIA goes a lot deeper than our small collaboration in quantum computing. And I wanted to just spend a little bit of time for this audience to talk a little bit about the broader relationship. So AWS and NVIDIA, of course, as many of you know, we have collaborated for a long time to deliver GPU-accelerated solutions in the cloud. And our joint innovations, they span topics from the infrastructure, software, to services, offering full-stack solutions in topics around machine learning, high-performance compute, and artificial intelligence. And I actually went back to look at the timeline of our joint launches over the years. And as a matter of fact, our collaboration goes back at least 15 years at this point. In 2010, AWS was the first to bring NVIDIA GPUs to the cloud with the CG1 instance type, the cluster GPU instance. And I actually looked at that blog post from that time in 2010. You can actually find it still online. And maybe unsurprising for this audience, but I found it interesting that there was not a single mention of machine learning or AI in this blog post. And that's a point I'm going to come back to. Yeah, but then we were the first major cloud provider also to bring the NVIDIA V100 GPUs with our P3 instances, and then again the A100 Tensor GPU instances with the P4 instances in 2020. And then just recently, last year, we launched the latest NVIDIA H100 and H200 GPUs, and we brought them to market in production as the first major cloud provider. And the P5 instances provide absolutely amazing performance. So they're 40% less expensive and 4 times faster than the previous generation of P4s. And we will look at a particular example of how we were using this state-of-the-art computational power of H200 GPUs to accelerate quantum computing demonstration in a collaboration that was done with AstraZeneca, IonQ, and NVIDIA together. But the broader point, why I wanted to go back to this broader relationship, is that today, obviously, thousands of customers are using NVIDIA GPUs on AWS and powering the most advanced AI and HPC workloads in the cloud in a variety of different verticals, from healthcare, life science, to automotive, media and entertainment, and the public sector. Right, so for example, Volkswagen Research Group is using NVIDIA GPUs on AWS for aerodynamic simulation. University of Oxford is doing cutting-edge research into artificial intelligence, and Netflix is building remote artistry stations for using AWS local zones and NVIDIA GPUs for low-latency artistry work. And this mass market adoption is fantastic, right? But of course, GPUs didn't start like any other technology. GPUs didn't start as a mass market technology. The GPU success story actually started in a niche application area of graphics rendering, just like that topic of that 2010 blog post was describing. And then the scientific community realized the same operations that people use to accelerate graphics rendering can be used in a variety of scientific compute topics, from fluid dynamics to genomics, and of course the then emerging field of artificial intelligence and machine learning. And from there, over multiple breakthroughs, of course, most prominently the emergence of large language models, GPUs saw the incredible mass market adoption that we're seeing today. So why am I telling you this? You probably know all this stuff. I'm telling this story because I think that conceptually, quantum computers will follow a similar trajectory. The first use cases of early quantum devices will be in the rendering of physics models, right? And I'm using the term rendering, of course, a little bit tongue-in-cheek, but it's really quite similar, right? So in these first use cases, you try to simulate quantum mechanical models that can be natively implemented on these devices, right? And you define the model, and that quantum computer produces something that you can observe, a measurement or something that gives you a different access to that model that you defined. So for example, when you look at analog quantum computers, like the Qiora device that we have on Amazon Braket, is exactly what you do. You define the system parameters in such a way that it mimics a model that you're interested in, a Hamiltonian that you're interested in, and then you can just let the system evolve and observe it at the end. So you give a different access to the model that you have defined. So this is kind of the definition of rendering. Yeah? And from those initial quantum simulations, it's not a far step to think about broader applications in scientific computing, for example, in high-energy physics, in condensed matter theory, and so on. Right? And of course, the reason why we're all here is because we all hope there will be the mass market adoption, the large-scale impact on a variety of industry. But which one will be this breakout application? I don't think we know yet. Could be materials, could be chemistry, AI, optimization. We have, of course, all our perspective on this, but the answer is still largely open. Yeah. And of course, this is where we want to end up, right? But I also don't want to downplay the applications at the bottom. At least, from my perspective, as coming from a scientific background, I think we should not underestimate and underrepresent the fundamental shift in our ability to understand and manipulate nature that quantum computers, once they are mature, will provide us, right? Quantum computers, first and foremost, are scientific devices in the near term, and a little bit like a telescope, right? Like a telescope allowed us to explore nature at a macroscopic scale, understand how planets move, how galaxies move. In that way, quantum computers will allow us to understand the microscopic nature, the physics at the microscopic scale in a completely new way, right? And that is why, again, in my opinion, we must pursue this technology no matter how long it takes, right? This is a fundamentally new compute technology. It's not just a little bit faster, it's conceptually different. And a new tool to understand the world that we live in, ultimately. And I don't think I'm the only one with that perspective, right? When you look at the supercomputing allocation in the US here, 30% of that is exactly spent on those types of quantum physics simulations that I had in these lower two buckets. And as a result, over 30 national quantum initiatives from governments around the world have been started, and countless more regional initiatives to drive research into quantum computing and development into quantum computing. And these scientific use cases are front and center of these initiatives. And a number of them are building with Amazon Braket and AWS to provide quantum computing and classical computing resources to local communities of researchers in quantum computing, with access to quantum computing resources, quantum computers through Amazon Braket, at the same time alongside scalable, elastic, classical compute from AWS in a scalable and secure research environment, and with all the administrative user access management and budget controls that AWS provides. But as excited as I am about the kind of scientific innovation that quantum computers will drive, ultimately we believe that in the fullness of time, quantum computers will have a broad impact on a variety of technologies and verticals. And in the fullness of time, in that world, we also believe quantum computers will be a part of the fundamental compute fabric of AWS. We will operate these devices probably in AWS data centers, in the fullness of time. And so in some sense, the long-term challenge for quantum computing is to make quantum computing boring. In some sense, we want quantum computers just to be another accelerator on AWS, right? Alongside GPUs, alongside AI/ML accelerators, ASICs, FPGAs, and so on. But of course, that is a long journey. This is not where the technology is today. And many of our customers are asking us today, what can we do? Where's the technology today? Is quantum computing a threat? Is it an opportunity? When should we engage? And if, how should we engage? Well, Marco Pistoia from JP Morgan Chase, he said, if a company doesn't do anything about the market right now, when quantum advantage comes along, it might be too late. And I love this quote from Marco, but obviously the word anything does quite a little bit of work here, right? If not anything, then what is the something that customers should do at this point of the industry? Well, the truth is, I don't think there is a single answer for this, right? It depends on every company, on the unique situation, on the ambition and the industry that they're working in. From when we think about the different types of engagements from enterprise customers, we try to structure it, though, along the typical R&D journey of a customer in industry. Right? From discovering use cases and generally understanding the technology on the left, to getting hands-on, implementing and researching algorithms and benchmarking them on quantum computers, to then not only implementing quantum algorithms, but actually pushing the state of the art, advancing the state of the art, developing custom new algorithms, publishing results, and so on, to then all the way on the right, lay the groundwork to envision and predict what will it look like for these algorithms to eventually be run in production. And we have customers that engage at all these stages. We already spoke about JP Morgan Chase, right? So they have a sizable research organization that are pushing original, excellent research into novel algorithms in quantum finance. So you would locate them more on the right. But we have other customers that engage maybe in a discovery session, see that the technology is still far out, decide, hey, it's a bit too early for us, go back to a monitoring position and re-engage maybe in a year from now. And that's totally fine. Right? Like, we want to support customers no matter where in the journey they are, whether they want to be thought leaders or whether they want to just de-risk themselves. So for that first step, to help with that first step, we recently launched a customer advisory program, which we call Quantum Embark. And that is really about helping customers understand if and when the technology will impact their business and help them understand the most relevant use cases in their vertical. It's a 12-week quantum readiness program with no upfront commitment. We have these 3 modules that you can take as a package or pick and choose a la carte around use case discovery, training and enablement, and then typically we have a deep dive where we take a state-of-the-art, a published result or something, and try to reproduce that and follow along the steps what it takes to implement a state-of-the-art research result. Yeah? So this program is really all about making quantum computing actionable and being very transparent about the state of the industry, helping customers understand if and when the technology will impact their business, but also arm them with the information that they need to inform their own stakeholders internally, whether it is, hey, we need to double down, we want to build a center of excellence, take the next step, or whether it is, it's too early, we take a step back. Both of these are outcomes that we want to support with the information that we can provide. And then in the next step, it's all about getting hands-on, right? Learning how to program quantum computers, implementing algorithms, benchmarking them on simulators, but also on actual quantum computers, of course. And at that stage, it's all about spotting opportunities and reducing risk, right? I don't think I'm telling any secret when I say that the technology is still very early. It's an early stage technology with multiple competing paradigms, multiple competing technology platforms and programming models. So it's very much about trying to reduce the risk or avoid technology lock-in, as well as reducing the cost of experimentation, right? Empowering your teams to try out different technologies, different approaches, and enable faster learning with the different technologies that exist and emerge. Yeah? And for that reason, this is what we try to provide with Amazon Braket. Right? Amazon Braket, as I said, is our quantum computing service on Amazon, on AWS, with the goal to making quantum computing accessible. We provide a choice of different types of quantum hardware, like AWS in general. Everything is pay as you go. There's no upfront commitment, no need to sign long-term contracts, expensive long-term contracts, as well as we're trying to strive for a consistent user experience. And I'm emphasizing that point, consistent, because we don't want to standardize, right? Quantum computers, we very much appreciate all the uniqueness and the unique capabilities of every technology, and we think that in order to really push the boundaries, researchers need access to all the different capabilities that these devices have, and it's way too early to standardize it, but we want to expose these capabilities in a consistent way, right? With a consistent API, consistent pricing model, consistent user experience in general. And today, Amazon Braket provides access to quantum computers from 4 different providers. This is IonQ and IonTrap quantum computers from the Aria and Forte system classes. We have superconducting quantum computers from Rigetti and IQM, as well as analog neutral atom quantum computers from QERA. So the QERA device we already spoke a little bit about is an analog device to emulate certain Hamiltonians, whereas the other 3 are based on the quantum circuit model. So we're trying to cover the main technologies and the main paradigms with our offerings here. And of course, there's frequent new updates to our portfolio of quantum devices. I'm particularly excited to announce today that we launched earlier today the latest device from IonQ, the Forte Enterprise, the latest device in the Forte system class, with 15 hours per day access over 5 days a week. 36 qubits, I think it's roughly 0.5% medium 2-qubit error rate. We have the experts here in the room, so you can correct me. But when I checked this morning, it was around 0.4 actually. All-to-all connectivity, support for quantum error mitigation. So we're super excited about this device. Okay, so in the next step, it's now all about pushing the boundaries, right? Like advancing, not only implementing existing algorithms, but advancing the state of the art, right? Doing original research into applications in a particular vertical. And one way that we're thinking about this is through a program that we launched that we call Amazon Braket Direct. And you see, the cloud in general tends to be hands-off, right? The general philosophy is to launch APIs and set your developers free. Let them experiment, let them do what they want. If a developer needs to reach out to AWS, it's a signal that we did something wrong. But this is not quite where quantum computing is at today. Innovation happens through collaboration. Innovation happens where the guardrails are loosened, where you try out different things. And so we wanted to acknowledge this state of the industry through this program that really allows customers to pull out the brakes and push these early-state devices to their limits, right? And it we provide dedicated access through this program to the different quantum computers that we have for the most complex workload where you only have access to, you are the only person having access to the device. We have ways to engage our scientists at Amazon Braket, as well as experts from the different hardware providers, such as IonQ or from QERA as well. And then we also think about it as an innovation sandbox, as a way to bring out new capabilities on devices faster than before, where we want to enable also our hardware providers to try out new capabilities in a more controlled environment. One example where we did that was where we worked closely with QERA to enable a set of experimental capabilities to unblock researchers from Oak Ridge National Lab and Purdue. So this is a set of features around, how big is the field of aperture on the atomic array that you can implement. The details don't really matter that much, but the point is that these features weren't quite ready for prime time. There were lots of limitations and caveats and things we needed to be aware of which is totally fine for an expert customers who is already an expert in the field of Rydberg atom computing. And through the direct interaction with QEra and our team, we were able to help them understand all these intricacies. But maybe it wasn't ready to expose to all of AWS customers. So experimental capabilities allowed us to bring this in the hands of these customers, and ultimately they were able to simulate quantum phase transitions in a particular type of physics model, the Shastry-Sutherland model, which is, by the way, exactly this kind of physics rendering idea and use case that I was describing before, and exactly one of the topics that Oak Ridge is very interested in. Another mechanism that we have to enable customers to push the boundaries is what we call the Amazon Advanced Solutions Lab. The Amazon Advanced Solutions Lab is a team of specialists across AWS, from quantum computing, high-performance computing, AI operations research, that engages in custom R&D collaborations with customers in order to build solutions for specific domain problems that the customers might have, right? And so we want to help customers primarily understand where quantum computing is at and deliver in a collaborative way new approaches to quantum computing, new algorithms, new protocols, but also help them understand what they can do on these very same problems with state-of-the-art and beyond state-of-the-art classical methods on AWS today. Right, so we're helping customers develop IP and know-how, trying to envision what is possible with quantum computing in the future, as well as what we can do already today with AWS. And so finally, I want to talk a little bit about what some of the challenges are that we think future quantum computing workload in the cloud will face and that we will have to address. Right? And of course, I think everybody is aware of that. The most important topic is the quantum hardware, right? Ultimately, the reason why we don't see quantum production workloads is because the hardware is not at the quality, at the error rates, at the scale that we would need to implement these algorithms that we know. So we're very excited to have seen last year a lot of breakthroughs in the field of quantum error corrections on different technologies, and we're especially excited about our results that we published about a month ago on hardware-efficient error correction with our first chip that we highlighted in this Nature publication that we call Ocelot. It's based on CAD qubits, so bosonic or oscillator qubits, hence the name. And allows for more efficient, hardware-efficient implementation of concatenated CAD qubit codes, right? That allows for up to 10 times more efficient implementation than the surface code. Yeah. So, as important as quantum hardware is, it is not the only thing that is important, right? Because when we look at a typical HPC-type workload, the question is, where will quantum computing sit in that stack? So this is kind of a schematic of maybe a computational chemistry workload or some other HPC-type computation. We have all the peripheral computations at the top, from the user interface, the user interactions, API interactions, data in and data out, the scheduler to orchestrate the different compute pieces. But then the music plays at the bottom here, right, where the numerical heavy lifting happens. And typically every workload has some components of different steps. Some of them might be interdependent, they have a linear dependency, some of them can be parallelized out. So there's different compute profiles that happen here, and this is what we try to optimize generally at AWS to provide the scalability, the elasticity, and the orchestration for these types of HPC workloads. And quantum computing is obviously not going to replace all of this diagram. Instead, we believe that quantum computing will eventually accelerate very specific pieces of this computational flow. But the rest of the classical compute will not go away, right? So in a sense, all quantum computing is hybrid in this sense, right? So it will always be embedded in a kind of classical quantum processing pipeline where quantum computers accelerate very specific pieces of the computation, right? And so this is one of the topics. This perspective motivated us and the NVIDIA teams to start thinking about what is the architectural vision about this future, right? And obviously, this is still a long time to go, but we want to think about what requirements arise from those ideas, right? And how do we build an architectural vision for QPUs embedded in scalable classical compute pipelines in the cloud? Yeah? As a first step, we started to work with the NVIDIA team to integrate CUDA Quantum and Amazon Braket. So CUDA-Q, obviously, as many of you know, is a programming framework that is developed by NVIDIA that combines QPU, GPU, and CPU resources in a single developer framework. And we worked together last year to launch an integration, make it available on Amazon Braket to provide scalable classical simulators based on NVIDIA GPU instances in the cloud, but also make accessible the quantum computers that we have available on Amazon Braket. So that was the first step that we took. But we also wanted to start looking into real-world examples and trying to understand more the computational requirements around these workloads. And we were very happy to start working in a collaboration together with AstraZeneca and our friends from IonQ and NVIDIA to build a proof of concept demonstration to model a Suzuki cross-coupling reaction with transition metal catalysts. So there's a lot of big words, but it's essentially it's a reaction type that is very relevant for medicinal science and drug development. And the way that we wanted to implement it was with a special type of quantum algorithm, which is QC-QMC, Quantum Classical Quantum Monte Carlo. It's a pretty mouthful, so I'll stick with QC-QMC, to estimate this reaction barrier. And we're going to talk on the next slide a little bit more how this algorithm works. And we did this demonstration with CUDA-Q, so the entire pipeline is programmed in CUDA-Q, and then using IonQ Forte on Amazon Braket, and then using post-processing, scalable post-processing on NVIDIA H200 GPUs on AWS Parallel Cluster to simulate this reaction. So QC-QMC is a quantum variant of a classical algorithm. So QMC, Quantum Monte Carlo, despite the Q in the name, is actually a fully classical algorithm. And I have a very schematic view on the different components, but you see it kind of goes back to this graph that I showed before, right? Because you have different compute steps in this process, from calculating the active space. Depending on the molecule, this might be known. You might be able to pull this off the shelf. But in principle, you can do DFT or Hattifog to calculate this active space. Then you compute the trial wave function. It's like an ansatz. And then you try to evolve that a particular decomposition of the trial wave function with imaginary time evolution. Details don't matter so much, but this becomes very compute intensive. And as a matter of fact, this creation of a trial wave function, if you want to simulate highly correlated materials, highly correlated systems, preparing a trial function that is effective becomes harder and harder on classical computers, right? So the idea of the QC-QMC algorithm is, well, we don't need to compute this trial wave function. We can actually just prepare it on a quantum computer, because we know we can efficiently create states with entanglement, with highly correlated states on a quantum computer, and we just measure them. All right, so there's an example. There's like one small step in this QMC algorithm that we kind of carve out, and instead of calculating it, we just prepare it on a quantum computer, measure it, and then everything in the pipeline stays pretty much the same. And yeah, so this is exactly what we did. So we used IonQ Forte 1 to prepare this trial state for 3 different molecules running roughly 60,000 single-shot match-gate circuits. And then, after this quantum computation was complete, we used NVIDIA sorry, it should actually be H200 Tensor Core GPUs. This is a typo here. In a cluster on AWS using AWS Parallel Cluster. 40 P5 EN instances with 8 GPUs per instance per molecule. So pretty sizable computation that illustrates how we need to scale out in the cloud. Yeah. And so the results of this work are still pending. We are still working on publishing the results, so I don't want to take away too much, but I still wanted to give a quick view on some preliminary results. And I think one of the take-home messages maybe is that the full end-to-end pipeline worked. We're able to bring this algorithm to converge. And to our knowledge, this is the largest implementation or the largest demonstration of QC/QMC to date, combining QPU resources on Amazon Braket with scalable classical compute from NVIDIA on AWS. And as a matter of fact, this post-processing step was previously thought to be quite prohibitive, right? Although this piece at the end there, right? The second part. Because previously it was thought that this is a severe bottleneck because while it's not scaling exponentially, it had a very poor scaling and large requirements. And through some algorithmic advances, the IonQ team was able to bring that estimate down. And then plus the acceleration with GPUs, we were able to reduce the time of this classical post-processing by several orders of magnitude. But again, for the full results, please keep an eye open for when the paper lands, and then we're happy to talk more about that. But I guess the main message, as I guess you have figured out at this point, is that I want to make with this slide is that future quantum computing workloads will be embedded in scalable and elastic HPC processing pipelines. In a sense, the notion of standalone quantum computing probably doesn't exist, right? There's always some kind of combination of scalable classical compute. And this is one of the challenges that we need to think about, how we empower users to run those large-scale demonstrations. What is the user experience around it? How can we make that a seamless experience? And we're excited to work with you and our collaborators from NVIDIA, IonQ, AstraZeneca to continue working on this topic. Yeah, so with that, I just wanted to give you a couple of references. So some of the things I spoke about, the Amazon Advanced Solutions Lab, our integration with CUDA Quantum, Quantum Embark as the first step in engaging in quantum computing, and Amazon Braket Direct on the bottom here. I did not mention our digital badge. That is a course, certified learning on quantum computing on AWS that you can take. And yeah, with that, thank you, and I'm happy to answer a couple of questions.
Thank you, Eric. Huge thanks for that. We have got a few minutes just for a couple of questions if anyone's got any, so please raise your hand and someone will bring you a microphone.
Testing? Yeah. So I have a question specific to the fact that AWS is essentially trivializing access to quantum computing. So how AWS filters bad actors? Is there some due diligence done?
Can you elaborate what you mean with bad actors?
Like, for example, criminals, if the criminals are interested in breaking encryption on something.
Oh, I see.
Using
I see.
your services.
Yeah. Well, I think the use case about breaking RSA, essentially, I think is the hardest use case that requires the most advanced quantum computers that are is deep in the future. So it's maybe a problem that is not quite as much on our radar yet. But of course, Amazon Braket is just another AWS services, and we have the same security and controls around Amazon Braket like with any other service. But right now, I think that use case has such high requirements to the quantum hardware that we're not too concerned. And then, generally speaking, yes, it's true. Shore's algorithm can, in principle, break RSA with a lot of qubits and with a lot of very high-quality qubits. And unfortunately, most of our internet encryption is based on RSA. It's not that there aren't encryption protocols that are, to the best of our knowledge, also unbreakable for quantum computers, right? So recently, NIST released the first standard in post-quantum cryptography. Many of these algorithms are already available on AWS. So it's a matter of implementing them over time. But yeah, that's
We've got time, I think, for just one more. Just take one at the front.
Fairly quick question. I'm just curious if you are planning to expand your support to other hardware beyond what you offer now, IonQ and Rigetti, et cetera.
Yeah, absolutely. So we're talking to a lot of providers. Probably we talk to all of the providers in the field in varying degrees of engagement. And when it's the right time and we mutually see an opportunity, we will absolutely onboard other devices, other technologies as they emerge.
Okay. Well, once again, thanks so much, Eric. I think that's a great note to end on. A round of applause, please. And so in this room, I can tell you what's coming up next. At the next hour, we've got a session from John Linford on accelerating end-to-end computationally accelerated engineering workflows. And then later in the afternoon, there's some more quantum sessions too. And if you like quantum computing, we've got our Quantum Day on Thursday at 10 a.m. Jensen's Fireside Chats. But again, thank you so much, Eric. And I hope you all have a great rest of your GTC.